Welcome to the Shika Serbu Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The topic of this video is automatic transmissions. Automatic transmission is composed of three sections: torque converter, shifting mechanism, and hydraulic control system. This video will provide explanations for these three components: torque converter, shifting mechanism, and hydraulic control. The function of a torque converter can be likened to two electric fans facing each other. A fan generates airflow, and it hits and rotates the blades of the other fan. In a torque converter, the rotating blades are referred to as the pump impeller, and the blades that are rotated are called the turbine runner. The medium for transmitting power is not air but oil, and this oil is referred to as automatic transmission fluid, ATF. In an actual torque converter, the flow of power makes a 180-degree turn. The power is transmitted in the following order: from the engine, to a drive plate fixed to the rear end of the crankshaft, to the torque converter case, to a pump impeller fixed to the torque converter case, and finally to the turbine runner that can rotate freely, which then outputs power to the transmission side. The inside of the torque converter case is filled with ATF. A torque converter primarily serves two functions. One of them is the power flow cutoff function. When the torque converter is rotating, applying brakes to the turbine runner allows it to stop the turbine runner, while the pump impeller continues rotating. This state is referred to as torque converter is slipping. This feature allows the engine to continue running, while coming to a stop at a red traffic light. Another function is torque amplification. First, let's observe the operation in cases where there is a significant difference in rotation speed between the pump impeller and the turbine runner, such as during launch or acceleration. For easier understanding, let's use a red ball instead of the ATF to explain. When the pump impeller rotates, the ball moves outward along the blade of the pump impeller, and then is transferred to the turbine runner side. At this point, because the ball also has velocity in the direction of torque converter rotation, it strikes the blade of the turbine runner, causing the turbine runner to rotate. The ball moves along the blade of the turbine runner toward the inner circumference, and returns to the pump impeller side. At this point, because the ball's velocity in the direction of torque converter rotation is slower than the pump impeller's rotation speed, when the ball strikes the blade of the pump impeller, it hinders the rotation of the pump impeller. This reduces the efficiency of the torque converter. To prevent this phenomenon, torque converters incorporate a stator between the pump impeller and the turbine runner. With the stator, the ball hits the stator blade and changes its direction before returning to the turbine runner. Because the ball's velocity in the direction of torque converter rotation is faster than the pump impeller's rotational speed, the ball pushes and accelerates the pump impeller. Through this, when there is a significant difference in rotational speed between the pump impeller and the turbine runner, such as during launch or acceleration, the torque converter can amplify torque. When the speed difference between the pump impeller and the turbine runner becomes small, the ball, which can change its direction by the stator, hinders the rotation of the pump impeller. To prevent this phenomenon, the stator is equipped with a one-way clutch. Thanks to the one-way clutch, the stator only rotates in one direction. As a result, when the speed difference between the pump impeller and the turbine runner is small, the stator rotates and the ball does not hinder the rotation of the pump impeller. Even when a car is cruising at a constant speed, because oil is used for power transmission, 100% efficiency can't be achieved, and it leads to decreased fuel efficiency. To prevent this, the torque converter is equipped with a lockup clutch. When under certain conditions, the lockup clutch mechanically connects the torque converter case and the output shaft. Control of the engagement and disengagement of a one-way clutch, and the generation of clamping force, are achieved by altering the direction of ATF flow in the torque converter. This graph illustrates the range where the torque converter locks up, based on vehicle speed and accelerator pedal opening angle. The pink area represents the lockup range for a model introduced in the 2000s, while purple represents the lockup range for that model's previous generation. The car with the pink range locks up the torque converter at the moment it launches, and maintains lockup during all driving conditions. Similarly to this car, since the 2000s, torque converters have been primarily used as a launch device rather than a torque amplification device. To understand shifting mechanism, it is necessary to first comprehend the mechanism of planetary gears and hydraulic multiplate clutches. If you are familiar with them, please use the seek bar to skip this chapter. A planetary gear consists of three components: an internal gear, a sun gear, and a planetary carrier. The internal gear has teeth on its inner circumference located on the outer side. The sun gear is at center. The pinions connect the sun gear and the internal gear, and the planetary carrier assembles the pinions. The pinions rotate individually, and also rotate together with the planetary carrier. Let's try applying the brake to the internal gear to prevent it from rotating, and applying an electric motor to the sun gear shaft for input rotation. The input rotation speed into the sun gear is reduced, and then output from the planetary carrier. When the electric motor is applied to the planetary carrier, the input rotation speed into the planetary carrier is increased, and then output from the sun gear. Next, let's apply the brake to the sun gear to hold it in place. The input rotation speed into the planetary carrier is increased, and then output from the internal gear. The input rotation speed into the internal gear is reduced, and then output from the planetary carrier. Lastly, let's apply the brake to the planetary carrier to hold it in place. The input rotation speed into the internal gear is reversed and increased, and then output from the sun gear. The input rotation speed into the sun gear is reversed and reduced, and then output from the internal gear. The gear is held in place by a hydraulic multiplate clutch. A hydraulic multiplate clutch consists of an inner shaft with grooves on its outer circumference, an outer shell with grooves on its inner circumference, and clutch discs that engage with each groove, and a pressure plate that exerts pressure on the clutch discs. The clutch discs engaged with the inner shaft can slide in the axial direction of the inner shaft, and rotate together with the inner shaft. The clutch discs engaged with the outer shell can slide in the axial direction of the outer shell, and rotate together with the outer shell. When the clutch is not engaged, the rotation of the inner shaft does not transfer to the outer shell. When hydraulic pressure is applied to the pressure plate, it pushes the clutch discs to produce frictional force. Then, the inner shaft and outer shell rotate together. Let's try installing a hydraulic multiplate clutch to a transmission. The outer shell is fixed to the transmission case, and the inner shaft is attached to the sun gear. When hydraulic pressure is not applied, the sun gear can rotate. When hydraulic pressure is applied, the outer shell and inner shaft are engaged, and the sun gear does not rotate. This is referred to as the sun gear being held in place. Similarly, the hydraulic multiplate clutch is connected to the sun gear and planetary carrier. When the clutch is disengaged, they rotate separately. When the clutch is engaged, the sun gear and planetary carrier rotate together as one unit. The shifting mechanism consists of planetary gears and hydraulic multiplate clutches. This automatic transmission is a typical 4-speed AT, with 2 sets of planetary gear and 5 hydraulic multiplate clutches. The left figure is a cross-sectional view, and the right figure is a 3D view of the planetary gears. The power from the torque converter is input into the rear sun gear, and output to the tire side from the rear planetary carrier. The rear planetary carrier and the front internal gear are always connected. In the P and D ranges, all clutches are disengaged, and the rear planetary pinions rotate idly, resulting in no power output. In the first gear of the D range, clutch D and clutch E are engaged, and the rear internal gear and the front planetary carrier are locked to the transmission case, preventing them from rotating. As a result, the input from the torque converter is reduced in speed by the rear planetary gear, and then output. In the second gear of the D range, clutch A and clutch D are engaged, the front sun gear is locked, and the front planetary carrier is connected to the rear internal gear. Similar to the first gear, the rear planetary gear reduces the speed, but the rear internal gear can rotate, resulting in a lower reduction ratio compared to the first gear. In the third gear of the D range, clutch C and clutch D are engaged, connecting the rear sun gear, the front planetary carrier, and the rear internal gear. As a result, front and rear planetary gears rotate as a unit, and the input rotation is transferred to the output without reduction. In the fourth gear of the D range, clutch A and clutch C are engaged. The rotation inputs to the front planetary carrier, and the front sun gear is locked. The input rotation speed is increased at the front planetary gear, and then output from the front internal gear through the rear planetary carrier. In the R range, clutch B and clutch E are engaged. The rotation inputs to the front sun gear, and the front planetary carrier is locked. The input rotation is reversed by the front planetary gear, and then output from the front internal gear through the rear planetary carrier. This graph depicts the progression of number of steps in an automatic transmission. By around 1940, GM had already developed a 4-speed automatic transmission. Subsequently, the era of 4-speed continued for approximately 50 years. Of course, during that period, there were also 2-speed and 3-speed automatic transmissions. In 1989, Nissan introduced a 5-speed automatic transmission, followed by BMW's 6-speed in 2001, Mercedes-Benz's 7-speed in 2002, Lexus's 8-speed in 2006, Land Rover's 9-speed in 2011, and Honda's 10-speed automatic transmission in 2015. Although the 4-speed automatic transmission had been lasted for 50 years, it evolved to a 10-speed in just 26 years. However, with the increasing adoption of battery EVs and hybrid vehicles, it is unlikely that further multi-speed developments in automatic transmissions will continue in the future. In other words, it might be said that historically, Honda's 10-speed is the automatic transmission with the most gears. In addition, as you have watched, a 4-speed ATs uses 2 sets of planetary gear, while 5 and 6-speed ATs uses 3 sets of planetary gear, and from 7 to 10-speed ATs employs 4 sets of planetary gear. The hydraulic pressure that actuates the hydraulic multiplate clutch is controlled by the valve body. Let's look at the operating principles of the simplified valve body. The valve body is installed within the oil pan of the automatic transmission, where the oil pump draws ATF from the oil pan. The ATF pressurized by the oil pump is separated into high pressurized line pressure and low pressurized pilot pressure by the pilot valve. The line pressure actuates the hydraulic multiplate clutch, while the pilot pressure activates the shift valve. When the AT control unit determines shifting, it energizes shift solenoid valve A to open the valve. This results in the application of pilot pressure to shift valve A, opening the oil passage to clutch A. Line pressure applies and activates clutch A, and then the transmission shifts to the gear A. When the AT control unit opens shift solenoid valve B, the pilot pressure activates shift valve B. The clutch B is activated. The engagement of both clutch A and clutch B results in a shift to gear B. When the AT control unit ceases power to shift solenoid valve A, clutch A disengages. With clutch A disengaged and clutch B engaged, the transmission shifts to gear C. In the actual valve body, as shown in this image, multiple shift valves and shift solenoid valves are incorporated into complex oil passages. In automatic transmissions, shift changes are achieved by combining the on and off states of these shift solenoid valves. Thank you for watching. If you enjoyed this video, please consider subscribing to our channel. We'll see you in the next video.